was trying to fix them. So I don't know if you can hear me. So let me start by checking the chat room. Confirm if you can hear me. Okay, yes. And also you can see the screen. Okay, fine. So, okay, good. Messages are flooding in. Fine. So I think now I have audio and I also have the screen being viewed. So let me just hope it won't be dropped anytime soon, because today we are going to rush into what we were supposed to do on Friday and also today. So I forgot that Friday was a holiday, and I woke up, I was ready to teach. Then I remembered it was Labor Day. But anyway, so today we'll just try to fast track. So last Monday when we met, we had started to talk about the conversation that we are supposed to have. And this is particularly on now machine learning itself. So we had talked on this. So these are slides for last time. There was an agenda here. This topic is called Introduction to Computational Learning Theory. And I had introduced the computational learning theory. So we talked about some certain things, and I was doing summaries as we were going on. So what did we discuss last time? So very fast, we discussed was things. The first thing is experience, then the task and the performance measure. You're just surrounding ourselves around terminologies, experience, task, and all these. So let me record now these tasks and about the recording. Fine. So if you were not there last time, you need to go through all these. We discussed some loss functions. I talked about what a loss function is and how a loss function is the quantitative measure of the performance measure. So it is just a way to measure how good our model is doing. And we talked about different performance measures that can be used in different tasks. So the performance measure depends with the task at hand. So if you're doing classification, we talked about that. If you're doing regression, we talked about that. So, and then we calculated F measure, we calculated all these. We talked about entropy, perplexity, mean absolute error, mean the squared error, which is very famous. And basically the interest here was the shape of the error curve. So you see like the shape, the way it flows. That is one of the most important things. We did these ones. Fine. So the next thing was the experience, which is just basically the data set. So no learning happens without the data set. Actually, if you don't have the data set, you either simulate or you just put the project on hold. So some projects are usually put on hold just because of the data set. Sometimes the cost of getting the data set is a bit high because you have to do a primary data collection. There is no data set, secondary data that exists, or the one that exists is not actually what you need. So data sets forms a basic and a very strong foundation. So no data, sometimes we are forced to just pause. So the more the data you have, the better. It determines what you can do. That's why people are mining a lot of data and all this. So fine. So either way, the type of data that I have will dictate, okay, how I can train my model. And this is what we actually call experience. So in supervised learning, you have both the data and also the label, which is the target. In unsupervised learning, you don't have the label, you don't have the target. So what is unsupervised learning and supervised learning? So the first thing you have to know is that data actually defines the kind of machine learning I can do. So in supervised learning, like we said last time, it's like you're just trying to learn a probability distribution, okay, of y given x. And we will talk more about this when we talk about probabilistic models. In unsupervised learning, you're trying to learn the probability of x, a distribution that describes x. And we talked about how the data set is going to be represented in form of a design matrix, okay, like this. And the rows and the features, which also call the columns. So actually we were today, not on Friday, we were to go now to, we take a break, jump to chapter 4, we discuss regression so that we see all this in practice, and then we will be back to computational learning theory. So very quickly, we jump to regression. Everything is on e-learning, the link, and the short notes. So now, today I'm going to talk about introduction to regression, then proceed with regression. So regression is one of the tasks. Basically, what regression is able to do. So this is what I'm just welcoming you from computational learning theory. And then I want to discuss today majorly linear regression. And we are going to train the regressor using gradient descent learning. And then we'll be back to computational learning theory. So fine. So basically through this, because you can read through, but I just want to explain the you need to know. And the aim of doing this is that I'm going to use this to tie to some of the theoretical aspects produced. So in regression is just a model that can be used to predict. And some of these predictions are like forecasting. You can do time series analysis, and you can just predict about anything. So you can predict how the markets will behave next, and you can just be able to predict depending on the data that you have. So the simplest form of regression, linear regression, and I'm going to use this to describe a linear regression is to try and learn. Okay, so you have a data set like this, and then you want your model to learn a line that bestly describes this data set. Now the line is the best possible line that when you measure the distance between every data point, so let me get a pen now here. When you measure the distance between any data point and the line itself, it should be the minimum possible distance from every possible point in the data set, minimum possible distance. So the line of best fit is like a summary or a rule, and this is what we are going in linear regression. So fine. So is linear regression the only option? No, actually, I'm going to tie so many other regressional models from linear to logistic regression and others that as we go by today and also on Friday. These ones. So, and then so we start with linear regression, a predictive model. It is a predictive model. We want to learn a line that basically describes data set. And then we use that line as an equation to do predictions as far as that data set is concerned. So fine. Now I want to remind you there is always a dependent variable okay? And then we have independent variable or variables, okay? These variables can either be continuous or discrete. Remember, we also talked about the scales, okay? Nominal or also going to be of importance. Now, dependent variable, you already have an idea what it is. So we will tie it to our example, independent variables. So independent, the one causing the changes in this one, okay? It's the one causing the changes. So now the independent variables can be many, but the dependent variable is always one. Okay, so if you're taking notes, that is one of the things that you might want to note down. Now, so let me see here. If the independent variable is one, it is called simple. Okay, you can read all this. So we want to fit a straight line in linear regression to the data set. Okay, so actually the official name for training a model, okay, is going to be fitting from today. So anytime you're training a model, you're just saying I'm fitting the data. So now we all know from our linear algebra and dealing with lines that a line usually can be described mathematically using this equation. Y is equal to mx plus c. So m is the slope of the line, and c is the y-intercept, the place where it actually cuts the y-axis. So today, I don't know if my mouse is going to do well. So it's technical hitches, not doing well. So assuming this is my Cartesian plane, okay, and plane like that. Then I have a line, let's say a different pen. So if I have a line like this one, that line can be described by that equation, and you already know. So the y-intercept will actually be here, where we are cutting the y-axis. So this is the x-axis. So actually here it's going to be the x-intercept. So fine, be that as it may. So the job is that we are going to fit a line, and that equation becomes important. So here, in this example, x is going to be the independent variable, and y is going to depend on x. So y is the dependent variable. Okay, so you can also take note of that. X is independent. Okay, so today I can't write much because I have been running a lot of models over the weekend. So this machine is just over breathing. So this is independent. This one is dipped. And yeah, there we go, freezing. To fit the best line to our data set, we need the best slope, number one, and also the best intercept. Those are going to be our two important variables, or should I call them parameters. So the aim of a linear regressor or a linear regressional model is to learn the best slope and the best intercept. Okay, so we are going to force the algorithm to learn the best M and the best C that well maps or fits to the data set. Okay, fine. So it's because of this that we define the error function. And I've tried to summarize this as much as possible. By the way, I write most of these notes just in my own words that you can be able to understand, so that it becomes actually. So we are going to use an error function. And the thing we are going to do is that we want to minimize the error. Okay, so the more you minimize the error, the closer you get to the best M and C. Okay, so the more you minimize, the closer you get. That best M and C, the best M and C, they are called the optimal values. So I'm looking for optimal values for both M and C. Optimal. Okay. Optimal. So my machine will be well back by Friday. Good. Then we are going to call iteration epochs. That's like the name that is normally used mostly. So for linear regression, we are going to use the mean squared error. Okay, this is going to be our later on as I discuss how to come up with a machine learning model. One of the things that you have to choose is actually your loss function. So you have to choose loss function. It is just the difference between the actual minus the predicted. So the predicted is called y hat. The actual is called y. From the equation, y is equal to mx plus c, okay, for linear models. So actually so we'll have the actual being y, like you see here, and we will have the predicted, okay, being defined by whatever m and c we have. Okay, so the closer we get to the actual, the smaller the error will be. So if y and y hat are the same, then the error will be 0. Okay, so that's the main thing. So this is the error function. So this regressional model learns by minimizing the error function. As you're minimizing the error function, you're trying to find the place where the error is the smallest. Okay. So the question is, how do we minimize the error function? So before we minimize the error function, we do a 3D plot of the mean squared error. So what we had last time is that not this one. What we had last time is a 2D plot. Yes, these ones. So this is a 2-dimensional plot of the mean squared error. You can see the shape. The 3D plot, which we will actually be plotting, looks like this. So this is the error plot, okay, or the plot of the loss function. So it is plot. We are going to plot a number of things. One of those things is going to be the error plot. So when you do a 3D plot, the error depends on two things. Number one is the slope that I have. Then number two, it depends on the y-intercept I have. And then that will define the error that I will actually have. So when you plot, this is the curve, and I have x plus c, but you can use any letters, okay? It's only that I used y is equals to mx plus c because you used that one way back. So that is how the error function looks. Now, to be able to minimize the error function is what we now discuss here. So the first point here that I wrote is that linear regressors learn by minimizing the loss function. That is the first important thing. So learning for linear regression or for regressors or for regression is by minimizing the loss function. So the question is, how do we minimize the loss function? So a minimized loss function means that we have discovered the best, okay, M and also C. And from there, we get the line of best fit. So to minimize the loss function, we need to compute its minimal value or its minima. And to compute, you actually need to compute derivatives. Minimal value or the minimum value can be gotten from the information on the first derivative. So now we need then now what we are going to do is actually compute derivatives. This is the information carried in derivatives. So if I have a curve, let me try to draw a curve. Okay, let's assume that's my curve. And I do the computation of this curve. Okay, so you can see the curve as like a number of turning points. This is mostly like a cubic equation. So what does the derivative tell me from our revision? Information, point A, okay, point B up here, point B, point C, and point D. So if I have the derivative, what can you say about the derivative on point A? Colin, then you tell me from your knowledge on derivatives, what can you say about the at point A? Positive, negative, is it rising, is it falling? You say. Your class. Someone to call in. What is let's start there. We'll need it from today onwards. What does derivative define? Yes, Jerry.
Hello, can you hear me?
Yes, we can hear you.
Oh, okay. Okay. I think the derivative
Yes.
describes the slope.
Very good. Derivative describes this. Good, very good. You wish to continue now and comment.
Slope.
So the derivative describes the slope.
Sorry.
Okay. Jerry, let's hear from Googie a bit.
Just to give it a short,
yes.
It's a positive slope that's decreasing.
So at point A, that is?
Yes.
So the point A, the derivative has a positive sign.
Yes.
Okay, good. I agree with you. So what someone's mic is on. You just have to mute. Now, the derivative is positive at point A. What does it mean? It means that it is
positive. What?
Yes, a positive slope means that the curve is.
Yes.
Yeah, I just want the word now. It is. It's easy, by the way.
Wait. Both the change in y and x are positive.
No, just on the curve alone. Is it rising or falling?
Oh, it's rising.
It's rising. Very good. So a positive derivative means that the curve is rising. Good. Quickly now, someone else to weigh in and tell us the opposite. Just rephrase the opposite so that we understand what happens at point C. So what happens at point C? or at region C. It's a region, it's a whole region. C is here. Is the derivative positive or negative? Is it rising or falling curve? Yes, Isaac.
Okay, at point C,
Good. So the curve is going downhill.
the slope is a negative.
The slope is a negative. Very good. There's actually
Downhill.
Isaac. Then finally, the most important part is point B. So someone to shine on this important point B. What's happening here? What's the slope?
For a moment,
Okay,
the slope is 0.
And the slope is 0. Thank you. Guys, those things are going to be important from today onwards. You're just about to see. So this point B is actually what we call the critical point. This is one of the critical points. So is point B a maxima or a minima? Anyone can just shout so that we know that we are doing well. Yes, Ngugi.
Maximum.
Yes, it's a maxima. Thank you very much. So you see, actually, the revision was worth it. I'll post the questions today so that they help you to go through. So this is a maximum question point. This is the minimal point or the minima we are talking about. So now I'm going to summarize a lot here, the calculus used in machine learning. So the derivative is actually important. It tells us whether the curve is rising or falling. If I only have the curve up to here, okay, so I'm speaking of from this point, okay, all the way to this point. So you see, actually, that shape is important. So if I have a curve like this one, okay, it only has a maximum, okay, a maximum. So even if you try to find a critical point here, the only thing you can get is a maximum. That's why we wanted our error function to look like this, okay, like this, with my mouse not being that accurate. So that is the point, let's say, from here. So that's why I was touching on the shape of the curve. It's important from here all the way to here, okay, that curve, like that. So that's why we were interested. Any curve that has a shape like this one is of interest. I like studying them. It's a potential error function. So it just so happened that the curve for mean squared error looks like this. So now we are just trying to find the minima of the curve, this point right here. And it's not easy because in every iteration, the curve shifts and changes and dances on the Cartesian plane. And that plane is not two-dimensional. It is 3D ongoing. In real world, you have even a million dimension kind of a thing. And you can't draw that. You can only do dimensionality reduction and then try to estimate a million dimensions in 3D. And you're going to see how rough gradient descent can get in such a thing. I'll show you some diagrams. So anyway, this is the model that we have here. So what gradient descent is going to do, okay, is going to randomly start at a place in this curve, okay. Then So it starts randomly, then it's going to try and find or to reach this minimum point. So if, like we have said, a positive gradient means that we are rising, and a negative gradient means that we are falling, okay? So gradient descent, what is gradient descent is now the next thing that we actually need to discuss. Good. The most famous way to learn in machine learning is using gradient descent. There's another way to train linear regressors. It's called least squared errors, but I'm not going to teach that. That's statistics kind of thing. But there is just a personal opinion. I am not very much fan of what guys call data science today, and that's just personal, and maybe I'll discuss that later. So now gradient descent is an iterative optimization algorithm. So what's optimization? Is when you are either trying to find the global minimum or the global maximum. Okay, so what did we, so before I go further, I want to ask from last time, where are my notes? Okay, fine. What did we call this shape? What was the name we gave to this shape? Someone who can remember. It's concave or convex? Anyone? You need to check. Yes, yes. There is someone whose mic is on. Monty. Yes. Yes, yes. You can hear me?
Yes, I can hear you.
Who is this?
Concave.
Concave. Okay, they said concave. Do we agree it's concave? Okay, fine. I need you to check up there in last week notes. So anyway, I'm going to be back to that also in a moment. So gradient descent. Fine. So we are going to minimize the loss function using a gradient descent. So what are some of the things that we need? Now, what does gradient descent do? It moves in a given direction, okay? Using some, so after identifying a place, okay, in the error curve randomly, it starts to move. That's why you say it's iterative. And it moves in steps. The steps, the magnitude of the step that it takes is called the learning rate, which we're also going to define. So there is a learning rate in gradient descent. We can cover more areas with a larger learning rate, but the problem is that we can overshoot the minima. So if you have a learning rate that is too high, you are not going to solve anything. And if your learning rate is too small, it's going to take a lot of time, okay? But now, if the gradient descent is able to successfully find the minima, okay, if it's able to find that point that we drew up there, this one, if gradient descent finds this point, we say that it has converged, okay? So the closer it moves to this point, the more it's moving towards converging. The more it moves farther from the point, it's called you're diverging, okay? So gradient descent needs to converge at this point. So if I have a too high learning rate, this is what you will find. They normally draw a famous thing like this one. It will keep on skipping maybe to this side and then to that side and then maybe returning. It's just random. It's confusion. There's a branch of maths called chaos theory that studies things like this. I don't want to teach it. So when the learning rate is too high, you have chaos like that. If the learning rate is too small, then you keep on moving in very tiny. Maybe you'll get there next year or something. You need GPUs, you'll be wasting a lot of computational time, etc. So if gradient descent finds the minima, we say it has converged. So how can we converge? Fine. So down here you can read. So now I take more time on the learning rate. So which is the issue, it will take more time. If the learning rate is too high, there is an accuracy issue. You will never hit, most likely, you will never converge at the minimum. In the machine learning and AI, you'll always be battling these two guys, efficiency and accuracy. And you must always strike a balance. No one has the best answer. So how can we balance these two things? So studies over time have been able to come up with some mostly commonly used learning rates like these ones that we have here. Okay, but they're just common learning rates. They're not like the best. Sometimes they work, sometimes they don't work. Sometimes they just overshoot. So if you have a very high learning rate, we are going to plot this one, by the way, it's going just to disappear. Kind of a thing. If you have a low learning rate, it's going just to lazy around. Okay, and so the best learning rate is going to give us a perfect kind of a drop, like you're going to see. So the learning rate is one of the things we have talked about. Then the next thing that we touch on here is the direction of gradient descent. That's why it's called gradient descent, because it has a sister called gradient ascent, okay, for the opposite optimization problem. So gradient descent is not a hill climber like gradient ascent. Gradient descent is a hill kind of, it goes downhill, okay? So gradient descent goes down. We have to fix that one because the traditional or the kind of normal gradient is that it always goes uphill, most likely. I will explain that. The need here is to force gradient to drop and drop and drop minima down here. So this is 2D, this is 3D. So gradient descent is iterates towards the minimum, like we are going to plot. Moving upwards, we are moving away. There's that point put here. If you are moving, okay, so you actually have to do the opposite. So you have to move downwards. That's why we say it's a downhill. Now, here is where we start. So before we do gradient descent, we have to talk about how to do the derivatives. Yes, I already now have an answer in the chat room. Yes, it's convex. I'll talk about it in a few. So now I want to touch on the concept of partial derivatives. Okay, partial derivatives, because that's actually what we are going to be doing from today henceforth. So we talked about derivatives. For example, if I have so a machine, I really pity the machine has been overworking. So if I have an equation, y is equal to, let me say, 2x, 2, no, that's not a proper 2, 2, maybe power 4, okay, plus 3x, plus 3x, 5. Okay, so this is the function. So we say y is equal to 2x power 4 plus 3x plus 5. So what's the derivative of this? This is easy. So y prime is equal to, someone to call in. This one you don't even need to calculate. We already know.
Power 4.
We will use the power rule. So what do I write?
X.
As we go. What's the first thing I write here? You remember how to do the derivative of polynomials. So this is 2x power 4. Let's start with that one. What's the derivative there?
I'm not quite sure. I think there's an answer in the chat.
No, I want guys to call me so that we have a one-on-one. Yes,
Hello, sir.
how are you?
Fine, thank you.
Yes, Solomon, how are you?
I'm fine, thanks.
Okay, good. Can we do the dy dx of this one?
Yeah. 8x power 3
Yes, this is going to be 8x power 3
plus 3.
plus 3. Good, plus 3. Yeah, that's the derivative. First order derivative, okay? Remember the power rule. So 4 times 2 gives you 8. You minus 1 here. This is power 1. So 1 times 3 is 3. X raised to power 0. 1 minus 1. 1. And then derivative of constants is always 0. This is the derivative of this function. But now let's compute the derivative of, let's say, now this one is not also going to be y. This one is going to be function. Okay, so function yj or whatever. Just x power 6, okay, plus 3 j, okay, j, my j is not proper, power 4 or whatever, okay, good. So if this is a function, okay, so this, what do we normally write this one? This one is written as function x, okay, it's a function of x, fx. Okay, so y is the same as a function of x, fx. But now down here, the function is not only of x, it's a function of x and j. So this is going to be function x, comma, j. So how do we do the derivative of this one? So anytime you have derivatives, you have equations with all partial derivatives, okay? So what we taught way back is derivative of one, okay, variable, like you can see the function of x. So partial derivative is actually when you have multiple variables involved rather than just having x. So there's an example I have put up here. You can have a look at that example and actually go through it. And to see how partial derivatives are actually done. So if I may pull this one is more clear. Pull, yeah, it's this one. So learning going downhill. Yes, it's here. So now the partial derivative. So if this is a function of x and y, x power 4 plus y 7. Now, partial derivative is done like this. This is powers. The guys were only taught maybe higher, maybe sometimes class of vectors, which I love so much. Or sometimes you can have a matrix. Now, if you have a tensor here, now you just take a few laps around the block, then you come back, because now such computations can actually be crazy. So, so we simplify things here. So partial derivatives is done like this. You're going to do, number one, partial derivative with respect to x, okay? That's the first variable. And then partial derivative with respect to y as the second variable. This is how it's written. This sign, you can read it as Kali D, or it has many names. Okay, so, or D, I like saying partial D. So when partial, when it's carrying, okay, exponents, coefficients, whatever, I just assume y. That's why it's partial. So if I assume y, I just do x, so it will be 4x power 3. That's the derivative with respect to x. The opposite is easy also. Derivative with respect to y, you turn off x and everything that it owns, and then you just do y. So you get y raised to power 6. That's an easy example of how to do partial derivatives. So anytime you have more variables here, okay, which are actually different, you need to do partial derivatives. So in machine learning, we use partial derivatives. So fine, using that concept, okay, and still we can just continue with the rules that we had. There was something called the power rule and the chain rule. So now from the power rule and the chain rule, we need to do the derivative of the loss function, okay? So remember, I will be alternating between the two screens. So this was our loss function. It's called the mean squared error. It's here, okay? Then we need to do the derivative of this function, the partial derivative of this function. And actually, if you do the partial derivative of that function, which I actually did by hand, it's easy. I want you to do the partial derivative. So what will you be doing? Because we want to learn M and C, you will do partial derivative with respect to M first. Okay, that means you are going to turn off C. And then partial derivative with respect to C, which means you're going to turn off F, not FM. Now, still the rules apply. So here we are going to use the chain rule. Okay, we're going to use the chain rule because you can see how the loss function looks like. There's a power here, and then there's a function inside here. So recheck the chain rule and actually how we do derivatives using the chain. This will be 2 will actually come here, and then the function. So then multiply this by now the first order derivative of the function. If you look at how the chain rule operates. So go ahead and check the notes on the chain rule. And then if you do the derivative, okay, so once, when you're doing the derivative, you can just forget this summation, okay? So when you remove this summation, also remove n, because this is getting the average after adding everything. So you just do the derivative here, then you are going to reintroduce back the summation, okay? and now it's going to be 2 over n because that power 2 actually came on this side. So if you do derivative partial d of partial d of m, so partial derivative with respect to m, which is the slope, you get that one. Partial derivative with respect to c, which is the y-intercept, then you get this one. Okay, so do the derivatives and actually confirm so that you're good to go. Fine. So after having known this, so we now have the partial derivatives, okay, for the squared error. So finally, this descent is going to do. So this is what gradient a partial derivative, and then it's going to force to move in the opposite direction. So we to update M and C. You see, we're going to learn the y-intercept. That's all we need to learn. So we need to learn the best M and also the best C, or the optimum M and C that describes a data set. So now here's what is going to happen. In every iteration, not introduce, but compute the error, okay? And then after running the derivatives, you're going to update M in every iteration and also C. So how do we update M? That's where now this formula comes in. So the gradient descent formula for linear regression is this one. Okay, so I am introducing now the official notations in C. So when writing scientific papers and machine learning, etc., the standard here is that we don't use M and C's, just using them for explanation. But these parameters are going to be called theta, okay, like you see here. And theta is, remember, alpha is the learning rate. We already know that. So what are we going to say here is that we have two members in this set of theta. The first one, so theta 1 is actually M, and theta 2 is C. Okay, it's just that notation, nothing to get scared. And how do we represent now the loss function? We just write the loss function as J, that's the function, and the arguments are theta, or even more specifically in this case in linear regression, J of theta 1, which is M, and theta 2, which is C. So this is what you will find in a standard way. So in summary, that I'm going to update M and C in every iteration, okay? So that I move closer and closer and closer to the C. So M and C, they're going to increase. The best M, the error, the better, the M, and the C. In this case, theta 1 and theta 2. So the small, then we are going to update the new M. Okay, so the old one is just, we just write theta 0 to say the old one. So if I'm updating M, I'll just have theta having a 1 down here and a 0 up here to say the old. So you can write that one. My pen is not doing good today. So anyway, it's just standard notation. So the old M minus the learning rate multiplied by, okay, so the learning rate multiplied by those derivatives that we have computed up there. The reason why we are subtracting is now what I'm finishing with in this regression before I tell you then. So if we go all the way back to what a gradient does, Okay, that's why I asked you about the story of positives and zero gradients. Gradients are actually interesting. I love them so much and they're very well applicable. So if the gradient is positive, it means I am going upwards. If it's zero, I'm flat. If it's negative, I'm going downwards. That's important. Please allow that to sink in. Draw this funny curve and these funny lines and have them somewhere. It will help you hours of trying to scramble for information from books, libraries, and internet, and watching many videos. I'm just summarizing these things so that you get it the way this in the simplest terms possible. So the gradient, when it's positive, we're going uphill. Now, because this is a convex problem, so we focus from here to here. If the gradient is positive, we are going in that direction. So we are moving away from the minima. If the gradient is negative, we are doing good, okay? We are falling. So now, gradients, when you compute them, ideally, this is the standard. So whatever gradient we get, we are going to negate that gradient, okay? So that if we are rising, okay, and remember the negative is also a positive, okay? Now, you have to tie that here. That's the explanation here. Is the reason why the gradient descent formula, we do actually the subtraction. So the subtraction is to move us in the opposite direction. Okay, so if we are rising, to fall. If we are falling, we want to maintain it like it is. So this is the formula of updating M and C, and that is going to be practically done, as now we have to actually be able to code this one. So we can also observe how the error changes. So number one, we want to ensure that in every iteration, the error is being reduced. Gradient descent is hitting the minimums, okay? So in order to see this, we are going to plot the error curve, okay, like this. So this is not the mean squared error plot. This is just how the error is behaving in every iteration or in every epoch. So as we do more and more iterations, how is the error behaving? Is it falling? Is it rising? So if gradient descent is working well, the error has to be falling. So you can see when we started, maybe in this example, the error was somewhere around 349. And then you can see it's falling in every iteration. So actually between the 0th and maybe the 25th iteration, there was a rapid fall. There's a rapid fall in the error. These are the things I like to highlight and study a lot. But now, then we study the error now falling slowly. Now, because of accuracy reasons and probably approximately correct, it never hits the 0 mark, okay? It just gets closer and closer and closer until we say this agent is, or this model is 99.9% accurate. Next time we will discuss overfitting and underfitting, and we'll actually be able to demystify that one. Fine, so this is how your error should look like. It should be in every iteration, naturally, not you forcing it to fall. It should naturally fall as gradient descent is in progress or in motion. So that's the to gradient descent used to train linear models. So before we go back to computational introduction how to code it. So part 2 of this class is going to be coding linear regressional model using gradient descent as the training algorithm. So we are going to fit the linear regression line of best fit using gradient descent. So you might want to head over to e-learning, either simulated data I have uploaded there. So very quick, today we build our first model. I'm going to give a 5-minute break and then I'll be back. But before that, let's log in here to e-learning. You see a couple of things updated. I'll put all these in one folder. Don't see like we have too much here. Now, we have machine learning task 1, linear regression. Okay, so you open this and read now. Okay, then you download dataset, small dataset we have here, and then we can be back in about 5 minutes. Now, before you go for the small break to take maybe a place coffee at your table, because now we are going to code line by line. We are going to code on Colab, so just head over to Google Colab, and we are going to write our notebook from there. You can do Jupyter Notebooks, but Colab is better. So you need a Google account. You already know that. Most students like Google, so I have no problem with that. And we are going also to use TensorFlow and everything from here. So actually me, I'm already logged in. So you can see I'm already there. So log in with your Google account. Then here, you just say new notebook, like that. And you can use the dark theme. Okay, you can see something here, but for me, I will just use the brighter one so that you see. And then that is going to be our interface of coding. You can also code offline, but a few things might be a little bit different. So right here, after we are done, it automatically saves this in Drive. So I will also encourage you, you can have a Drive. So you see, actually me, I normally work, yes, I work on my machine, but I have Google Drive for desktop. It's on for Windows. You can check for Mac. And actually I have all my files here. So whatever I'm working on locally just automatically updates. So you can see my updates are always running, and I can access these ones from in work or here at home or wherever I go. I always just do everything and I leave them there because either way, because me, I had a Drive for desktop already, so actually just brought here automatically. Fine. So either way, we will have a lot of installations. That's the beauty here. For if you are using Jupyter Notebooks directly, you might need to do a few pips, okay, here and there. But either way, doesn't hurt. So we'll be back here shortly. You download that, download this data, place it on your desktop, and then we'll be back with machine learning task 1. I can do it like halfway, then you will finish. And then there is a guide here. You can also download this one and have it. So I think we can be back in like after 5 minutes after you've prepared all those things. Don't log out. We are still on. Like in the morning today. So this is simulated data, should be the same one that you have. So let me just try open the Excel. So it's a simple data set. Okay. So the thing here is that we are assuming this the office prices or monthly rent for an office in Nairobi. And we are also assuming that the price or the monthly rent for an office in Nairobi is determined by the size in square feet. So you see, that's why I labeled this one, the size in square feet, and also the price. So very quickly, by just looking at the data, someone to tell me what is the dependent and what is the independent variable. Those are going to be important. So we start there to tie everything we have discussed to this exercise. So what is the dependent? Is it size in square feet or the price? And which one is independent? Is on no 1353 or Isaac? Yes, whoever goes first. Isaac?
Okay. A trial.
Yes.
So for me, I think price depends on size.
Okay, so we can actually even construct a sentence. We say the price of an office in Nairobi is on the size, and that one makes sense. Yeah, very good. Thank you. So it's just we relate it to real life. The price of an office. How much do I pay for a monthly rent in an office? For an office. And someone can tell me it depends with the size. Okay, so that word depends actually is very natural occurring in a sentence. The price depends on the size. So the price now becomes the dependent variable, and the price, it's the other way around. So the price depends on the size. So size is independent and the price is dependent. Okay, so now this is what I call a one-dimensional problem. The price depends on the size. Okay, now I need one person to tell me, if I was to rent an office in Nairobi, what are other factors? Okay, apart from the size, what else? Yes, Julie.
I think the location also will matter when you're renting out an office or when you rent an office.
Very good location. What else? Very good. So Julie says, John, that's perfect and true. What else could be the other factor? We can do this fast before we code. Yes. Okay, available. That's Vanessa. I think it sounds familiar. Different name here. There's a chat room here. Okay. Condition of the office, though it's a bit general. Location. So me, I love tea, so maybe that will be a price driving factor. The interior, is it furnished or is it just empty? I have to come with my furniture and all these things. So all those things, you see, all those aspects are driving the price. Okay, so price is only one. Okay, So price is dependent on many factors. So that's why we said the dependent variable is always one, but independent variable can be variables. They can be many. The more variables you have, the more complex the problem. Okay, some variables are important, others are not important. That's where we will have to do. We will have to trim out some variables. We will have to say, now I don't. Okay, we'll have to do feature selection. I'll teach that on Friday. So some features are more important than others. Why? So I can say maybe when I'm looking for an office, size is the main driving factor of the price. So we are going to see the size is going to be more important maybe than the interiors and so on. That one for Friday. For today, we have a one-dimensional problem, only the size on the x-axis and on the y-axis. So if you're writing notes, you can say your x is the size and your y is the price. So we rush quickly through this, and then I will leave you to finish and upload maybe your notebooks. So now, apart from that, I have prepared a very small guide here. I know some of you are already familiar with this, but I like doing it for uniformity so that we move together. So in this task, so let me just open the one in my machine so that it looks better. Task, you are going to use three so in this task, these are pandas. That is for creating what we call data frames. So this is for data organization, access manipulation. This is my own definition. So I have put up a link to the official tutorial on pandas. So I'm just going to open these links. The first one for pandas, please open the links. For matplotlib is going to be the one we use for graphical plotting and visualization. This is where we are going to see our line of best fit. Actually, so we click on that one, the MATLAB, no, the matplotlib, which is related to MATLAB. Okay. Guys in machine learning don't like MATLAB that much, so Python, we love Python so much. And NumPy for our vectors, matrices, numbers, distribution, we are going to use NumPy. So actually today we are not going to this is a simulated data set. Okay. Now I want you to write this one if you're taking notes. The closer the data set is to regressional. So this is just a data set generated, okay, using the Gaussian distribution. The other name for Gaussian distribution is the normal distribution. And you remember the properties for normal distribution is that it had a very perfect shape, if you can remember. So if the data is having a Gaussian distribution, then that's when the regression will work the best. New data set, we'll be generating our own. We'll be writing Python script to generate, these are 100. Okay, so we'll be generating 100 numbers that are normally distributed. And we use it as our training data set. Fine. So that's where NumPy will actually come in. So, okay, fine. Now, I'm not sure what Jayden wanted me to, if it's on the Gaussian distribution, I will be back to it. But it's just that we can use NumPy to generate to generate. The closer and closer. Okay, fine. So the more the data, training data that you have, Yani, the more that data is closer to a normal distribution, okay, the better your model will be, okay? So I like to explain it in the simplest terms possible that you can actually be able to get. You remember the shape of Gaussian distribution, which is also the official name for normal distribution. It was bell-shaped, okay? I don't know if my pen is back. So that distribution looked like this was, no, my pen is still not doing well. Remember that shape. Good. So a lot of real-world data set follow the normal or Gaussian distribution like that. It means that if I collect data, a lot of numbers are concentrated towards this place. You remember this was the frequency. Okay. If I may draw something larger, the frequency. Okay. And are all equal. The measures of central tendencies are all equal in a Gaussian distribution. In short, it has some special properties. Though it's not usually perfect that a data set will follow the Gaussian distribution. Some data set will be slightly skewed. Okay. No, disappeared. Others will be closer and closer, and so on and so forth. So the closer it is, the better the model will be. Okay. So it's part of the declarations I will discuss later, how to prepare your data. If I have a data set that is not normally distributed, how can I convert it into a form that is almost a normal distribution? I'll discuss those techniques. It's part of computational learning theory. Fine. So very quickly, let's do this. So let's go to our notebooks. How did I press that one? So my screen disappeared. I hope I'm back. So here we are going to do the following. So we just doing the imports. Okay, it's closer to my controls. That's why this one. Then I expand it. Fine. It's very fast. So we have said 3 libraries. Okay, 3 libraries. It's here. So we start by importing pandas. Okay, just type, it's easy, you already know this. Import pandas as, you can say pd, import matplotlib. Normally do plt, and then finally import numpy, okay, as np. So are going to be famous libraries. Then you can click here to run to see if actually the imports are okay. So if you're using a Jupyter Notebook, sometimes you have to peep a few of these. I don't know if they changed, and that can be hectic. Also, if you are coding, or you can't just say import pandas, you must have pandas, okay, or numpy, you must have it. So actually that one worked. So I just click here on code to go to the next cell. Okay, so that's step 1, import the libraries. You can see it's actually automatically saving. Fine, so later you will rename it, okay, into something, okay. Maybe linear regression. Okay. like that. Fine. So the next thing is that we can then actually initialize the things that we need. So we'll be moving fast to the nodes. So you see in the nodes, we have said in regression, we will need to train the model so that it recognizes the best slope and also the best y-intercept. So those will be my first things to initialize. I'll just say m is equal to 0. Okay, we normally just start at 0, and c is equal to 0. Those will be the initial points to start. Then in this, my example, I discover that the learning rate that will work for a better explanation, because you're not going to do many iterations, is going to be 0.0001. Okay, I don't know if my screen is I have zoomed in. Okay, zoomed in. Zooming means I've increased this. We need to initialize the iterations epoch. Okay, we can define any number that is. So I'm just going through actually what I was able to write. Fine, so there won't be a problem here. You can run that one. Then we do the next cell. So in the next cell, we want to access our data. No data, no machine learning, okay? To help us to access, we need pandas, okay? How do I read and write tabular data? Okay, that's where I came. So okay, you're familiar with all these. So if you're working offline, we normally just say, okay, and just say familiar the CSV by just saying PD, what we imported up there, CSV. Then you put the URL to where your CSV is on Colab. That's why I was able to. And these ones could be changing over time, so we always just need. Good. So you check these below. So creating subplots, we'll do that. When I need to read data frames locally, you can check that, but let's use this one. So this is famous data science site. Someone has written an article here. You can read through on how to access, okay, differently. So we just go directly to this one. Okay, so I'm on Colab, which is online, but I want to access CSV that is actually in my machine. So the code line there is from google.colab import files. So you can type that one before we do this one. So from google.colab, okay. And you can actually see like the software is always going to be doing some suggestions here. So it's actually just like the interactive one that you normally use. So you then say import, okay. So import, can see. files. Okay, fine. Then you do the second line here. Uploaded is equal to files.upload. Dot upload is a function, and you run that one. Okay. Then if we run that one, we find that it asks me now to get that file. So go to your machine and actually just get where you have downloaded, okay, and unzipped that which we had. So mine is here. So you just click on it, and then it will upload. It's a small data set. Okay. So you don't need to cram these ones because they keep on changing as new versions are released. So what you always need to do is to always have the documentation all the time as you keep going. So now we have the data, so we can now proceed with the next step. Okay. So data is equal to, so like now we are working locally. Okay. PD, okay, dot read CSV, and we are actually just going to say, because it was called data, so data dot C. Yeah, so you notice how our data looks like. Where is that? Okay, we have this and that. So because we have this and that, I just want to tell these column that the first, okay, you see the first row is actually just the header. So I just put, the easiest way to do that is just say header is equals to 0, like that. And you can see all these are arguments that you can pass, okay, in there. So be this as it may, let's run that one and see. So we have our data. You can try to visualize the data according to that article that I've shared, data.head. You can say, I want to see the first 3 rows. Okay, then you run that one. Okay, you see the first 3 rows. You can say, I want to see the last 3 rows. They are giving a function called tail for that. Okay, and you can actually run that one. And then you see the last 3 values here. Okay, so as we are not going to visualize, so we are going to put something else here. I think so far so good. I hope no one is lost. So now we have the data. So let's just define what will be our X and what will be our Y. So use large X and Y because there is a reason for that. For large X, can just say data because we already have it here. Depending with what you named here, it's a variable. Okay. And then down here, I can say data. Okay. Good. So move up, move up. Oh, okay, fine. I have suggestions you can actually see. So no, we say that Y is going to be the price, and then you can see where the. Okay, fine. Delete those ones. Okay, fine. Good. So now we just need to say what is X and what is Y. I didn't cram that one. Where's my Excel? Fine. So this is going to be my X. I can put it just here. And then that is going to be my Y. So we're just preparing it. Good, so we have x and y, okay. The next thing we will need, because of the formula, okay, so this is what I did. I just defined n, which is equal to the length of x, okay. How many do I have? I know it's 100, but what if the data changes? Then I want this to be float. Just something simple. Okay, fine. So I have a question here on the chat. Okay, fine. Okay, control plus space prompts the autocomplete. Okay, fine. So now, okay, fine. So we have x and our n here, which is just the length. Then now we go to the next cell. More controls there, control and B. Fine. So these ones, we want to write linear, shortest lines possible. There's so many codes you can get online, etc. But I just like coding these things from first principle. We won't be doing this, by the way. We won't be coding from first principles. Likely, this is the only model in this class which we will code from first principles. We did coding for neural networks from first principles time. So we'll actually be using TensorFlow, etc. Fine. So now, fit. Okay, this is the main thing. So I need like the line of be able to do all these computations. Good. So we now write the main function. Okay, the function you can say define thing. Mine I call it gradient descent fit. Okay, I'm fitting the model. Okay. I first defined y hat, okay, like that. It's going to be equal to m times the linear equation times x. X is a vector. It has many values in it, plus c, okay. Y is equals to mx plus c. That's how we get the prediction, okay. So this is the predicted value, y hat. So that's the easiest part that I saw. Then the next thing is actually to get the derivative of the error, mean squared error. Okay, so we done it on the paper. So we just code it here. Okay, we can just say the derivative with respect to m is equal to, so the formula that you're seeing there, it's 2 over n. Okay, so just a moment. 2 over n, can put that inside the brackets so that BODMAS we are sure to be followed through. And then actually is 2 over n and the summation of negative x, etc. So I will just bring that negative here. So you see values multiplied by k. Can just do as it is there on the slide, and y minus mx plus c is actually the y hat, so y hat, like that. So that's like the derivative with respect to m from the slides, just copy pasting, typing it here. And also type derivative with respect to c, which is the same as Also, there's a negative here. By the way, you need to do these partial derivatives by calculation so that you see. So negative 2 over n, and I've already done the negative there, so I just multiply by the sum, and this is going to be y minus y hat. Okay, so we are coding a bit slowly because they're quite a number. Fine. Anyway, after doing the derivatives, we say the next thing that will happen is to update. Okay, so in every iteration, so we need the iteration. So here I'm just going to say for I in range. Okay, so depending with the epochs that I have, okay, like that. We need to obey indentation, and I'm just then for every epoch we will be updating m. So we'll just have the new m is equal to the old m minus learning rate, like we have here, multiplied by d over the one you have computed up there. Same for C, the old C minus learning rate either way, multiplication will take place first. Good. You can just do some spacing for clarity. And yes, I think that's the major part of main algorithm. Then after we are done, we can return whatever we want to return. We can even print. Okay, you can print the finals. M is M, and maybe the final C is C, so that we see the final. Okay, sorry, right here. Final M is very easy. The aim of the program is not to print. It is actually to come up with a line of that one first. So I'm doing here. So this guy will need arguments. The first argument, they will need to know what M is. This is redundant, but I fit all this. Let's see, the guy needs to know what N is. And what else does he need? He needs to know what L is. And basically that's it. Okay, just run this one. Want to do anything, to just be fine. Good. So by now you already know how we are moving. And yeah, someone is asking me to go back to the PD read section. It's easy. You can just follow through. You just code these lines and browse to get where you have downloaded the file. You must have downloaded that data from eLearning. And then this code is just here in what I shared. Okay, it's the same here. So it's actually easy. Okay, good. So that one is fine. Do the next cell. Now I can call this one and do the plot. So here I can just say PLT. Remember what we did up here. Okay, matplotlib.pyplot as PL. Okay. When you scatter X and Y, this is actually how that data set looks like. Okay, the X and the Y. Why am I typing scatter? You can just look at the tutorial here and just see everything. plt.ylabel. By the way, we can just start defining things like these ones. Okay, you can just say, please, now here you can move faster than me. plt and then dot y label. And our y was monthly rent in shillings. It's just an easy example. Okay, fine. So you see how now our data set is plotted here. Okay, scattered, just scattered. And we want the line of best fit that best describes this data set. Good. So after viewing that one, so we have X and Y. And the next thing that we want very fast, I'm moving fast, maybe in 10 minutes, give me 10 minutes, then I will leave you to continue, take lunch as you also prepare for the next class. What will be the next thing here? So now I have X and Y. I need to call gradient descent fit. Okay. Redundancy again, just pass all that you need to pass. Okay. And let's wait a minute. We can just pass all these as defined up there. And it will not do you any harm. So M and C, they are 0. Okay. N, which is the size, and L, which is the learning rate. Now this function, we have set it in such a way that it returns something. So I'll just say y hat is equal to that. Okay. Then that will learn and then return whatever best y hat we have. So we can just now say plt dot plot. Okay, this is linear regression in the fewest lines possible. And when you're doing the plot, again, you can check there on what I've shared. There's no magic here. By now, you're a computer science person. You already know how we do all these things. Fine. So the best way we just did this one for the line is just saying I need the minimum values. Okay. So of x, okay, and its maximum value of also x, it's big X, and then minimum value of the predicted just function. There are many ways to plot all these anyway. Okay. Okay, fine. So let me see how many iterations are we doing. 100, not much. And actually, so when we run that one, you see this is the line of best fit that was able to be created. This is the final M value, and the final C value is here. It means this equation, say y is equal to 1.4788x plus 0.03507, whatever. You can color this one. You can just say color. Which color do you like? Here is where ladies might help us. Here I'm always colorblind, so let's say black, which is the universal color, primary color. And I just, yeah, so the line is now black. And that is 100 iterations, okay? Okay. Then, so that is part one. Any questions on any cell? Cell 1, 2, cell 3, cell 4, 7, 8. I think so far so good. This is easy. Good. So the next thing that we might now do is, because we want also to plot the error. Okay, so we want also to plot the error. So I plot the line of best fit. You can do an animation and see in every iteration how the line is emerging from here and going all the way up. Okay, you can do an animation, but as we just did, the final line is what we are plotting here. Okay, so yes, Joseph. No, I don't think guys are new to Python. We did a lot of coding back then. I know you guys know. If you're new to Python, the group work, someone was coding a lot, yet others were not. You need to code these ones. So just get familiar and go to python.org and start writing. Now, as we are not using, yes, we are using Python, but now this is IPython. You can also check out what is IPython, what are Jupyter Notebooks, and who is Google Colab. And you just takes a long day up to speed. Anyway, this is a simple plot of and then you get the line some two plots, okay, on both the, I want to plot two things. Number one, I've plotted the line of best fit. Number two, I want to see how my error behaved. Okay, I want to see how my error behaved. So I will have two plots. I can have three. I can plot the line of best fit, which is the main thing. Then I can also want to see how my mean squared error is like. These are 3D plot. I'll talk about 3D plots from maybe Friday or next Monday. So I won't plot that one today. Just want to plot the next easier one. I want to plot the line of best fit, and then I want to see how the error is. Was it actually reducing? Good. So to make two plots, that's why that's the final part. Creating subplots using matplotlib. So this is what they have on the, you can click on it and open it. Okay. The tutorial. Okay. The best one that I picked here is this one. So we do something closer to this one. So you can scroll up to there. It's going to have a figure and two axes or axes. So, and then you can put a super title. There are ways I have used to do smaller titles. But first we start by doing these ones. So we no longer use PLT as it is, but up here on this cell, I found it easier to do it on this cell. We can just say the figure now, okay? And we can have our two axes. The syntax is in the documentation, axis 1 and axis 2. Okay, so the first axis is for this that we have done. Second axis is for that error that we want. plt dot sub plots. Graphs to be, so I just type 2, so it's there. Okay, then now I will make the first axis to be this one, what we have just done here. Okay, and the second axis will now be the error. So instead of having PL, I will have AX1. Okay, so there is a better way to define now these labels, PLT. So there you will define the labels, then the documentation. Yeah, again, this one, wait a minute. So again, this one will be AX1. So X2 dot what? So come back here very quickly. We are extending actually because of, so you need two things. The epoch number of iterations you have done sits on the x-axis. So I need to, so in every iteration needs to sit on the y-axis in this curve. Okay, so always check which curve am I plotting. Okay, so this is the error decreasing curve. So it means in every iteration I have to arrest two things. Number one, I have to arrest every error computed in that curve. Different ways of doing this. Coding is both an art and a science, but I like doing complex things in the fewest lines possible. At the back of every iteration. Okay, so the first list, you can just call it epoch count list. It's equal to, no, I will just append. Okay, appends can be risky. I will say why, but I'll here in every iteration. Okay, and just pick the number 100 and have it going. But I need to see 1, 2. I need to tie this one. You can use a dictionary to zip the two. Okay, I need to tie this one to the error. Okay, so in every iteration, I want to arrest the iteration number, and I also arrest the error. On epoch dot, not dot. So want to arrest someone, and just have another cell, define error. Okay, that's the main thing that we used. So quickly, how was mean squared error computed? That's the error. So you remember from the notes, the mean squared error is usually, okay, the value for y that you have minus the predicted value. You're going to square that, and then you're going to get the average. Okay, so we just code that one the way we coded the part. It's an easy thing to do. The other return, I'm just going to say 1 over n multiplied by the sum, okay, of y minus y hat. I'm going to square that. Good. that will be our mean squared error, but the guy needs to know what n is. Also, the guy needs to know y is, redundant again, and the guy needs to know what y hat is. Good. Fine, so okay, that is, let me see, it's fine. Okay, fine. So now, after having all that, so I can call that here, okay, MSE, and then I pass all this, and then it will calculate the error for me, y and y hat, pass those arguments. So that will be the epoch error. Then I need to arrest that error and store it in a list. So I'll just say epoch error list. These are variables, you can call them anything, but I like calling variables what they carry. Dot append. Okay, fine, then I put epoch error in there. Good. Now what append keeps on adding in every iteration. The dangerous part of it is that after running this code once, then I come back, I run this code. Does it, you're only doing 100 iterations. So the easiest way to do that is not to append to the original list in memory, but to do an instance, but I don't want to go through all that. There are many ways to do what we just did here. Fine, so then down here, so axis 2 is going to plot what is sitting on the x-axis. So I can just say epoch count, okay, list. Fine. Then that's the x-axis, and then the y-axis is just the epoch error list. Epoch error list to sit on the next axis. Now, the problem here could be that all these, they are happening in here. So maybe they have a local definition. So now actually when I run that, it will error. So I have just to say, I need another initialization here. Initialize those lists. Epoch error list equal to an empty list. And then epoch, what was the other one? Iteration count, epoch count list. It's going to be also empty list like that. Fine, so now the next thing that you need to do is actually now to plot and everything. No, I didn't run this one, so I need to run that one. Good, the rest are okay. So I'm also shutting down, so don't worry. That one is fine. I think this one was fine. Yes. So you see, actually, now we have n of best fit, and actually we also have the error. You can decorate these ones more. You can set color here. I want you to put labels here. You say, and the main label up here. So I want you to read through what I just shared. Where was that? Yes. No, for subplots. We'll be using a lot of subplots to just kind of plotting multiple ways. I drag. Say fig dot super title. You say this is my linear regression. Then to do yeah, you can actually set. Okay, you can set titles. Good. So I already set my titles offline. So due to time, I can just grab them as and then finish this one. They are for X1. Okay, so you can do all this. Good. Just ensure you don't mix tabs and spaces. You can cry all night trying to fix that error. Yeah, I think that one will work for my AX1. Then for my AX2, set your own titles. You can. Okay, so if I do, okay. Either way, that's the most basic way. You can see after I ran the second time, you see how this is misbehaving. Is because of the problem of appending. Okay, so the append can really mess your life if you don't know you're aware. So actually my append now around now has being because it keeps on appending on the old variables created in memory. Okay, so you actually start seeing this is not even making any sense right now. Double the light regression, and you now have your not personally and actually just start coding. So the key question here, 1 minute, then I address issues, then I will go through. So let me see. Machine learning task 1, okay. Good. So train an intelligence and so on. Predict the office price when the size is 100 square feet. So someone to tell me how do we go about this? Okay. So now we have the line of best fit. How do we now predict? Now this is the main reason why we need the model. So that predict. It depends with the number of iterations that you did. For 100, let me see, what did I calculate? Where is this, my calculation pad? Do 1,000 iterations, then you tell me what is the office price and how you actually got that one. Then we will be good to go. Okay, someone is like calling in, so let me see. I went so fast.
Plus, most of us feel saturated and
yeah, I know the time. Even my voice is gone.
Yeah, please.
I'm just thinking of lunch. I understand it's a difficult time. But I hope guys were able to follow through just the step by step. You can redo it, by the way. I think I'll provide a notebook. Okay. But be careful of the append. It will do some funny things. So be careful of the append. You can destroy, after every iteration, you destroy the list so that it clears it and it becomes new again. You can destroy. There are many ways to handle that. That's why I say you have to know your way through. You can destroy the list just before you end down here. I can reset the list so that in the next iteration now the lists are the same. Either way, I want you to learn as you write this one. Okay, fine. I will upload the notebook and then you'll be good to go. I want someone to give me the value, assuming, okay, fine, because maybe you are not able to finish, assuming these were the last values for M and C here. Okay, sorry for that. Scroll down. Assuming these were the final values for M and C. So how do I predict the price if the size is 100 square feet? What does this what does these values mean? What is the equation of the line of best fit?
I think you just need to replace 100 square feet in X.
Okay, very good. That should be Vanessa. Yes, but first let's write, Vanessa, first let's write this equation is equal to mx. So what is m? It's 1 point, yes?
1.47.
Yeah, we do 4 dp. Guys, you can write this one. Good. 1.4788. And then our x here, right? The one that you said.
100.
So 100. So x is 100. I'm writing slowly because also my machine is tired. I'm going to just shut it down after this. So y is equals to mx is 100 plus c, right?
Yeah.
So our c was 0. Anyway, guys, thank you, Vanessa. So guys, calculate that value. Y is equals to mx plus c. So y is equals to 1.4788 times 100 plus 0.035. Which value do we get? Yes, Jaden. Okay, so help us to interpret that one now. Very good. I like when you start mentioning divide by, but now remember here, this was price times 1,000 shillings. So we just multiply that value by 1,000. Which value do we get now after multiplying by 1,000? Jaden?
147,000 roughly.
147k. Okay, so actually it makes sense, right? So if 100, so we had a square feet of 100 here. So the model is just we never 47 point something k, okay, in Kenya shillings, and that's the essence of a predictive model. We will do more with predictive model next time. I'm going to introduce more independent variables. So please, before Friday, go through these ones. Before Friday, check on e-learning, some exercises on hand mathematics. On the videos, I am really working on it. Won't pass this week. And thank you. More questions? By the way, you can set up your team and also contact me weekdays. Can set up another meeting on Microsoft Teams and chat more on AI and then we can. So I'll upload this one right now on e-learning. All the best. x and then